In the last video, we defined what a vector space was. And in this video, we'll look at a first example of a vector space. So just to remind you, to define a vector space, we need to first define a set V. Then we need to define the two operations that we'll be using. So we need to define some sort of addition and some sort of scalar multiplication. And then we need to check all 10 axioms that we just saw, the 5 addition axioms and the 5 multiplication axioms, the ones we saw in the last definition. All right, so that's what we'll do today. We'll do it for this specific example. So example 1.1.4, I'm going to look at the set, which is Rn, of vectors with n entries, all of them real numbers. So of n-dimensional vectors with the usual vector addition and scalar multiplication. I want to check that this defines a vector by verifying each of the 10 axioms. All right, so we're going to need elements u, v, and w for v. Let's give them names so that we don't have to do it every single time. So I'm going to assume that my vector u is a1, a2, an. My vector v is b1, b2, bn, and my vector w is c1, c2, cn. All right, I'm going to start with the first axiom. I'm going to need to prove that if I add two elements in v, I'm going to get another element of v. So let's add v plus w. Usual vector addition, so I'm going to add the corresponding entries. And since each of these is a real number, then what I get is still inside v, which we said was Rn. I'm still getting a vector of n real numbers, and so axiom 1 is true. Axiom 2. In axiom 2, I need to compare v plus w and w plus v and check that I get the same thing. All right, so v plus w, we have it right above. I have b's then c's. If I do w plus v, I'm going to get the c's first, the b's second. Oh, sorry. It's hard to not copy what I have right above. All right, so C2 plus B2, Cn plus Bn. Almost did it again. All right, so I want to know whether these two are the same. Remember, all of these are real numbers. And in real addition, I'm allowed to switch the order. And so these are equal. Properties of real numbers. And so yes, v plus w is equal to w plus v. All right, so this means hence. All right, so I'll be using these 3 dots to use hence in proofs in the future. All right, so that's axiom 2. Let's look at axiom 3. In axiom 3, I want to compare u plus v plus w with the same expression, but with the parentheses in a different spot. So let me spell this one out. So I'm going to leave u out here, and then I'm going to add v and w, which I've already done a bunch of times, so let me just add that. And then I'm going to add these. So I'm going to get the first entries, A1 plus the whole thing I had here. So I'm going to place this here. I'm going to need parentheses to make it precise. All right, again, these elements here are all real numbers. And so I know that I can switch the order in which I take the addition. I can take the one between A and B first, and then the one in C. Same thing for all these entries. So again, because I'm writing it in terms of the entries, which are real numbers, here I'm actually using a property of real numbers, which we already know is true. All right, so then the last element that I'm adding is C, and so I can split it like this. And then this first one here is A1 AN plus B1 BN plus C1 CN, and so I am getting this is U plus V plus W. All right, good. Axiom 3 is right. Let's do axiom 4 right here. I'm sorry, I'm a bit tight on space. I have the whole next page, but I have a lot of axioms. All right, so in axiom 4, let's get back to that page. In axiom 4, I need to find a zero element. So I need to pick an element in V that doesn't change anything when you add it to your other elements. So in this case, I'm going to take the zero vector. That's going to be my zero element, and we know this from linear algebra, so let me just write it out, whether I add it on the left or on, sorry, V plus 0 is 0 plus V is just V. All right, axiom 5. I need to find an inverse for every element. So any V, I need to find minus V. Of course, we already have it in linear algebra, and I need to make sure that if I add it to V, I get the zero vector. That's easy, so take minus V to be minus B1, minus B2, I just flip all the real numbers, minus V plus V, or V plus minus V is equal to B1 Bn plus minus B1 minus Bn, and that's going to give you 0, 0, which is the zero vector, which is our zero element. All right, that's it for all 5 addition axioms. Now I need to look at the multiplicative axioms. So first one, I need to look at what happens when I multiply V by K. I need to make sure that I'm still in the same set Rn. Well, I still am getting real numbers here, so these are all real numbers. And so this is in Rn still. All right, so axiom 6 is true. My set is closed under scalar multiplication. Axiom 7. Let's check. I need to check that whether I do K times V plus W or I add KV and KW, I get the same vector. So let's spell both of them out. KV plus W, that's K, and then V plus W is going to be this element here where I add the B's and the C's. So I can multiply the K inside. Sorry, a bit tight. And then I can multiply it in using what I know about real numbers. So all of these kind of come down to what we already know about real numbers. And then this is KB1, KBN plus KC1, KCN. And so that's KV plus KW. And again, the main step here is when I distribute the K on this, but this is again on real numbers. So it's not about vectors anymore, it's just about real numbers, and that's something we've proven in high school, and so we already know it. All right, axiom 8 and 9, you'll do on the worksheet. Axiom 10 is pretty straightforward, so let me do it here. I'm sorry, I actually put a line through my H. All right, axiom 10. That one is just about what happens when you multiply by 1. It seems pretty trivial, and for most standard example, it's going to be true, but it's easy to come out with an example that fits all other properties and not this one, and that's not something you want. You don't want 1 times v to be something other than v. And so we expect it, and so it's part of the axioms. So I want to look at 1 times v. I'm going to multiply b1 through bn by 1. That's not going to change anything because those are real numbers. And so I get v back. All right, so we checked 8 out of the 10. I'll let you check the final 2, but all 10 axioms hold for v, which is Rn. And so we have a vector space. Which is good because that's the example that we're trying to generalize. So if it didn't fit for this one, we would have the wrong definition. Let's give this a name. We're going to call it the Euclidean vector space. So the vector space Rn with the standard operation will be called the Euclidean vector space of dimension n. To make sure that we don't confuse it with just a set Rn, on which we could put other operation. This is one specific set with 2 specific operations. So whenever we mean Rn with these operations, we'll call it En, E for Euclidean. All right, another thing is in the worksheet, we'll show that it's enough to prove reduced axioms for axiom 4 and 5. Instead of proving, so let's look at 4 and 5. Instead of proving that v plus 0 and 0 plus v equals v, it's enough to just prove that v plus 0 is v. And the same thing for the inverse. You only need to prove one of the 2 additions. That's enough. We'll see why in the worksheet. All right, so in the next video, we'll be looking at examples that are newer, right? So not Euclidean.